Hello everybody. So we are going to, in this video, wrap up chapter 5, and which was about normal distributions. However, this by no means ends our use of normal distributions. In fact, this last section is going to be a nice little application of normal distributions, namely using them to approximate binomial distributions. Now, if you remember, just last chapter, if x is a random variable with a binomial distribution, x represents the number of successes in n trials in which the probability of success on a single trial is constant at some number p. And we, on our calculator, we use the commands binom PDF and binom CDF to compute various probabilities. But this is a discrete random variable, so we can use a histogram to actually illustrate the probability distribution in this case. And where we have these rectangles, where each rectangle has width 1, and the height basically corresponds to the probability that x is equal to whatever corresponding number it is. So, like, for example, this rectangle right here, the area of this rectangle represents the probability that x equals 2. This rectangle represents the probability that x equals 3, and so on. Now, you'll see that in some cases, actually in many cases, if n becomes very large, and if we were to plot all these rectangles together, you would see that it kind of looks like a normal distribution, a normal curve, in the sense that the tallest rectangles are in the center, and the shorter rectangles are towards the end. And think, okay, well, because it might be seem like a lot of calculations when n gets very large, if you want to find the probability, that x is in a certain range, and you have maybe 100 rectangles to count and to compute. Is there a little more efficient way of computing this? Well, will a normal approximation be just as good? And it turns out many times there is. For example, in this case, this shaded area represents the probability that x is either 2, 3, or 4. That is, the probability that x is between 2 and 4. Now, notice here that this shaded region, this actually begins halfway between 1 and 2. It's a 1.5. And it ends halfway between 4 and 5. That's 4.5. Now, if we were to look at the corresponding area under a normal curve with these same boundaries, in which a normal curve which would have the same mean and standard deviation as the binomial distribution, then maybe that might work as well. Remember that by this binomial distribution, its mean will be n times p, and the standard deviation will be the square root of npq. So if we take a normal distribution with this mean and this standard deviation, we get this curve, and we can look at the corresponding area. And it turns out that in certain situations, this area on the right will actually approximate the area on the left, which of course represents the probability that x is in a certain range. And it turns out that the only thing we really need is two things to happen, that np and nq are both at least 5, where, remember, q is 1 minus p. And I think we have that right up here. Yeah. So as long as np and nq are both greater than or equal to 5, then the binomial distribution can be approximated by the normal distribution, where the mean and standard deviation is np and square root of npq, respectively. Now, the only challenging part would be, well, what are the boundaries? What are the endpoints? And really, the thing here is we just either need to add 0.5 or subtract 0.5, depending on what the situation is. If we want to find the probability that x is greater than or equal to a and less than or equal to b, then our boundaries will be a minus 0.5 and b plus 0.5, just because of the situation like up here. Because if what we're trying to do is here's A and here's B, and then the rectangle, here's our rectangle at A and our rectangle at B. Okay, we're including all this area here, and you know this region will start at not A but at A minus 0.5 and goes to B plus 0.5. If we want to talk about the probability that x is greater than or equal to A with no upper bound, then we just use the area under the normal curve to the right of A minus 0.5, right? Because again, we're in this situation. Here's A, and here's another rectangle and another rectangle, and we just continue going over here. So it's to the right of not A, but A minus 0.5. And then finally, if we want to talk about the probability that an area, that x is less than or equal to b, this is the area under the normal curve to the left of x equals b plus 0.5. Okay, we want to make that crystal clear here. And that's because we're in this situation. Here's b. Here's our rectangle and more rectangles here. Okay, so here our boundary is right here at 0.5. BB plus 0.5. Okay. By the way, just so you know, this thing is called the adding and subtracting of 0.5 is called a continuity correction. Okay. All right, that's the only real tricky part. Okay, because like I said, the mean and the standard deviation we already know. So let's look at this example here. So now here we have a biased coin in which the probability of heads is 0.37, and is tossed 100 times. And we let x equal the number of heads. First question you want to ask yourself is, can this be approximated by a normal distribution? Well, let's say identify what n, p, and q are. N is 100. If we define a success to be a head, the probability of success is 0.37, and q would be 1 minus 0.37, which is 0.63. Okay? Then np would be 100 times 0.37, which is 37. That's certainly greater than 5. And nq would be 100 times 0.63, which is 63, and that's bigger than 5. Okay? So the answer is yes. And our mean, or our mu, is going to be 37, and our sigma is going to be, the standard deviation is the square root of 100 times 0.37 times 0.63, which is approximately 4.828. Okay? So this is what we want to use in the normal CDF commands. So if we want to find the probability that, let's say, of between 40 and 50 heads, and that's being inclusive, this will be the probability that x is between 40 and 50. This would be the area under the curve between 39.5 and 50.5. So we use normal CDF of 39.5, 50.5, and then the mean is 37, and the standard deviation is 4.828. And so that's what we want to plug in. We do not want to plug in 50 and 40. Okay, so we compute this, and it actually turns out to be right at 0.30%. Okay, so Now let's see what is the probability of at least 35 heads. That means x could be 35 or greater. Okay, so this would be, so now the continuity correction, this is the lower bound, so we'd subtract 0.5 from 35. So this would be normal CDF of 34.5. And then there is no upper bound, so we just take infinity, which we can take to be 10,000 in this case, if we want. And then the mean is still 37, and the standard deviation is still 4.828. We enter that into our calculator, and we get 0.698, or about 70%. And then what would be the probability we have fewer than 30 heads? Fewer than 30. Now, you want to read this carefully here. Fewer, that means 30 is not a possibility. So the greatest it can be would be 29. So this is really the probability that x is less than or equal to 29. So this would be 29 minus 0.5. That would be, well, that would be the upper bound, rather. So this would be 29.5. So we add 0.5 to this. So this would be normal CDF of, well, the lower bound is negative infinity, so we can take that to be negative 10,000. Then we said the upper bound is 29.5, 37, and 4.828. And this is approximately 0.06. 060. So 6% of the time you'll have fewer than 30 heads, or 29 or fewer heads. Okay. Again, if you're a little confused by the continuity correction, you can draw a picture. Here's 29. Here's your rectangle, and this you're including that and all the other rectangles, right? So this would be 29.5, and that's where this comes from. Okay. So this will actually be very helpful in the next chapter when we do confidence intervals. So do your homework, get lots of practice, and we'll see you next time.